You know, your car is having literally thousands of conversations every single second. It's this hidden, invisible network of data that keeps everything running, from the engine all the way to your windshield wipers. But what happens when that conversation stops? Well, today, we're going to make the invisible visible. We are going to dive into this secret network and explore a totally revolutionary way to find problems when they pop up.
Seriously, just think about that for a second. What if you could see not just the wires, but the actual information flowing through them? And what if you could spot a problem not by looking for what's broken, but by seeing the heat it gives off when it fails? Okay, let's dive right in. So here's the game plan. We're going to start with car's nervous system. Then we'll learn its language, see what happens when it all breaks down, and then, this is the really cool part, we'll uncover a powerful new diagnostic tool through a fascinating real-world case study. Right, so to understand how a car actually talks to itself, we first need to get acquainted with its central nervous system. And it's not a single brain, not at all. It's more like a network that connects, well, everything. It's called the CAN bus, which stands for Controller Area Network. Now, back in the day, you would have had this massive, heavy, and super complex bundle of wires running from one central computer to every single little thing in the car. But the CAN bus? It lets all the different systems, the engine, the lights, the bodywork, talk directly to each other. This was a total game changer, simplifying the wiring and making the whole car way, way smarter. But the CAN bus is how it protects its messages. See, it uses this twisted pair of wires. When a message goes out, the voltage on one wire, the CAN high, goes up from 2.5 to 3.5 volts. At the exact same time, the voltage on the other wire, CAN low, goes down from 2.5 to 1.5 volts. It's this perfect mirrored signal, and this design makes it incredibly resistant to outside electrical noise. It ensures the message gets through loud and clear. Okay, but those voltage changes aren't just random electrical blips. No way. They're actually a highly structured language, a series of digital ones and zeros that are organized into sentences that every single component on the network can understand. And this is what one of those sentences, they call it a data frame, actually looks like. Now, I know it seems pretty complex, but stick with me. We're just going to break down a couple of key parts that make this whole system so efficient and, frankly, so robust. First up is something called the arbitration field. The best way to think about this as a system for deciding who gets to talk first. So a message from your anti-lock brakes, for example, is obviously way more important than a signal from your radio. This field gives that critical brake message priority, making sure it gets heard immediately and preventing any data traffic jams. It's really clever. Now, the real heart of the message is in these two fields. The data field is the what. It's the actual information, like, hey, 2,000 RPM. Then you have the CRC, or cyclic redundancy check. This is a brilliant little error checker. It's basically a math problem that gets sent with the message. When the message arrives, the receiving module does the same math. If the answers match, the message is good. If not, it's ignored, and a new one is sent. So that's how it's all supposed to work. But what happens when things go wrong? You know, when there's physical damage and the network suddenly goes quiet? To find out, technicians have traditionally turned to a tool that lets them literally see electricity, the oscilloscope. And this right here is our baseline. This is what a healthy, perfectly functioning CAN bus looks like on the screen. See those perfect, clean, mirrored square waves? That's the CAN high and CAN low signals, clear as day. That, my friends, is a happy network. But look what happens here. On the right, the CAN low wire has shorted to ground. It's completely flatlined at 0 volts. But the network is smart. The CAN high signal is still, so the system is able to limp along in a less reliable single-wire mode. The converse for sure, but it hasn't been completely. And this is a catastrophic failure, and it's illustrated perfectly. The CAN high and CAN low wires have physically touched each other. That critical voltage difference between them, the differential signal, it just collapses to 0. And the network goes completely silent. No data gets through. It is a total communication breakdown. Now, looking at waveforms on an oscilloscope is powerful, no doubt, but it takes some serious technical skill. But what if there was a more intuitive way to see a problem? What if instead of looking for voltage, we started looking for heat? This brings us to a really fascinating concept called emissivity, just a fancy science term for how well something gives off heat in the form of thermal radiation. And the cool part is, with a modern thermal imager, we can see this radiation. The camera turns that invisible heat signature into a vivid picture with a whole spectrum of colors. The physics behind why this works is actually super simple and elegant. It's a chain reaction. Anytime you have electrical current flowing through a circuit and it meets some resistance, work gets done. This creates what's called a voltage drop, and that voltage drop generates a byproduct we can easily see with the right tool, heat. So where there's an electrical fault, there's very often an unusual amount of heat. All right, let's put this all together in a real-world detective story. This is a case involving a Ford Expedition that rolled into a shop in the dead of winter with a totally dead battery. This is a classic parasitic drain problem, and trust me, these can be an absolute nightmare to track down. But instead of spending hours testing circuits, the technician tried something new. First, he just pointed a thermal imager at instantly. Bam! One fuse was glowing way hotter than all the others. Second, he put an amp probe on the battery cable, and it revealed this rhythmic 7-amp pulse. Something was trying to turn on and off. The wiring diagram for that hot fuse pointed to the rear wiper motor. And finally, the smoking gun. The tech pointed the thermal imager at the rear liftgate, and there it was, glowing white-hot right through the interior trim panel. The motor was seized, totally frozen solid. It was trying to move but couldn't. It was drawing a massive amount of current and generating an insane amount of heat. This was a 5-minute, completely hands-off diagnosis of a problem that could have taken hours to find, all by making that invisible heat signature visible. Just incredible. So, does this mean is the magic bullet for every electrical problem out there? Well, not quite. Like any powerful tool, you really have to understand its strengths and its limitations. For instance, in really hot climates, the engine bay might be so warm that it just masks the heat from a fault. Shiny surfaces? They can act like mirrors, reflecting heat from a hot part nearby and totally throwing you off. Even your own body heat can mess up the reading if you're not careful. The key takeaway here is that it doesn't replace good diagnostic strategy. It's just another incredibly powerful piece of the puzzle. From the silent, lightning-fast language of the CAN bus to the invisible story told by heat, modern cars are constantly communicating with us. This journey from invisible data to visible insight really shows us that the biggest breakthroughs don't always come from looking harder, but from learning how to see what's been there all along. So it makes you wonder, right? What other invisible stories are just waiting to be told?